Hello everyone, welcome to BlackHat Europe Arsenal. I am Furkan Göksel, and in this presentation I would like to introduce my new polymorphic encryptor tool called Shoggoth. For the next 30 minutes I will explain its concept, its methods and its features. As you know, files written to the disk can be detected before they are executed with the help of signatures written for them. Although various encryptors and packers are used to bypass these signatures, after some time, all other variants become detectable when a detection rule is written for the static decryption routines used by these tools. To avoid such a static unpacking or decryption routine and to generate statically undetectable binary payloads, I developed Shoggoth. So first of all, let me introduce myself. My name is Furkan and I am from Turkey. I work at Picus Security as a red team engineer. It's a breach and attack simulations company and I am a part of the Windows endpoint team there. My research interests are red teaming, vulnerability research and operating systems. Besides, I love developing small projects for newly discovered red team techniques in C and NIM languages. I'm sharing them from my GitHub and Twitter accounts. You can reach me and my projects from these handles. So, what we will have today. First, I would like to mention the idea behind polymorphism and its implementations. Then, I want to make an overview of the Asmjit project, which is the main part of my tool. After that, I want to introduce and explain the technical features and methods of Shoggoth. These are PE loading, COF loading, and their loader implementations, garbage code generation, and two available encryption methods. Then, I want to show you the general execution flow by using a diagram. Later, as a demo, I will analyze generated outputs for a PE file, a BOF file, and a raw shellcode. In the end, I will quickly summarize what is my plan for the next versions. So, let's begin with the polymorphism idea. In general terms, polymorphic or polymorphism means to exist in various forms of different types at different times. It's a widely used term in many areas like biology, object-oriented programming, or mathematics. For cybersecurity, this word means a malware's ability to create numerous encryption-decryption routines without modifying the underlying code in order to disrupt the signature derivation mechanism. This means that since there will not be a single constant algorithm or a key, a signature that will cover all variants cannot be easily written. Generating different code blocks for each encrypted variant is based on randomness. In polymorphic encryptors or polymorphic malware, the part that creates different routines according to this randomness is called mutation engine. Mutation engines increase the probability space by using methods such as subroutine reordering, dead code insertion, and register swapping to produce different code fragments. Since the methods mentioned here are about low-level programming rather than high-level, mutation engines work directly at the level of assembly instructions, and their outputs will be architecture dependent. Although this concept was first seen in the chameleon family viruses, as anti-malware and threat detection technologies developed, such packers and encryptors started to become widespread. Considering the techniques used by mutation engines and their outputs, there are some requirements for them. These are dynamic code generation, content change, operation code randomization, and value insertion. Shoggoth meets these needs with the help of a library called Asmjit. Asmjit is an open-source lightweight library for machine code generation written in C++ language. It is developed and led by Petr Kovalicek. It can generate machine code for x86, x86-64, and other architectures. It's still actively developed and improved. There are a lot of open-source famous projects which use Asmjit for their needs, like x64DBG, Blend2D, Cinder, and many more. Asmjit is a very big project and has advanced features for its users. Since Asmjit allows specifying operation codes, registers, immediate operands, call labels, and embedding arbitrary values to any offset inside the code, it is one of the most suitable libraries for a polymorphic encryptor's needs. Asmjit works like a state machine that can be controlled by function calls. There are API functions implemented by Asmjit that correspond to each assembly operation and its appropriate operand types. As these API functions are called, Asmjit saves the corresponding assembly instruction with given operands in its internal buffer. After the Asmjit objects are ready, it is sufficient to call the API corresponding to the machine instruction, just like writing an assembly source code file. To illustrate its usage, I want to give a simple code-based example. Let's say that we want to generate the following assembly instructions by using Asmjit. In the desired code block, we first put 1 in the RAX register, then push the RBX value to the stack. We are summing the RCX and RDX values. Finally, we add the value in the stack to the R8 register with the pop operation and call the return instruction. To assemble these instructions, we need to initialize Asmjit internal objects. First, we initialize the JIT runtime object, which is the main controller for Asmjit. After that, we create a code holder object for holding code and other relocation information, and we initialize code holder with the JIT runtime object. For assembly instruction generation, we generate an assembler object and attach to the code holder. You can tick that these 4 lines are the default prologue for Asmjit initialization, and now Asmjit is ready for generating desired assembly instructions via assembler object. This object contains an API function for each operation code in the architecture-dependent instruction set. Therefore, for each line of the assembly code block that we want to generate, we call the corresponding API functions with the operands, like move function, push function, add function, and so on. After the last API call, which is ret in this case, you can call the add function of the JIT runtime object, and that function copies the code from the internal buffer of code holder and returns an address for the generated code block with the executable permissions. Now we have covered the Asmjit. Let me dive deep a little bit into Shoggoth. I want to talk about how it works, its features, technical details of the features, and general execution flow. So, Shoggoth is a polymorphic encryptor tool for different executable types. It's written in C++, and for any dynamic code generation needs, it uses the Asmjit library. So, we can say that polymorphic decisions are implemented with that library. It works on 64 bits binaries. The output of the tool is the encrypted version of the input file with its decryptors. Currently, the output format is a raw shellcode file, and to execute, you should combine it with a loader or injector. There are 3 input modes right now, which are raw mode, PE mode, and COF mode. The difference between them is, if you choose raw mode, it doesn't add any loader stub for your payload. However, if you choose the other 2 modes, Shoggoth appends loader stubs which were precompiled. There are 2 different types of encryption in Shoggoth, which are random block cipher and RC4 cipher. Shoggoth combines both of these encryptions by default. And lastly, Shoggoth adds different garbage instructions which don't have any side effects to increase the probability space and remove the possible signatures. You can read Shoggoth from the link below. Now, I would like to explain the technical details of the features I mentioned briefly here. As I just mentioned, Shoggoth can work in raw input mode, as well as in PE and COF modes. The difference between these modes is that a loader in the form of shellcode is integrated into this payload and encrypted together to run the input file. Therefore, when the output file is run as a shellcode, it will also execute the given COF or PE file. For PE loading, the appended shellcode will do the following steps. it will first allocate an executable region with the size learned from the size of image field. And it will copy the decrypted PE headers to that region. Then, it places PE sections to their corresponding relative virtual addresses. After that, it finds the PE's import directory and parses it to resolve required imports. If the allocated region is not the PE's preferable address, it will fix the relocations from the relocation table. When everything is done, it directly calls the entry point and starts the execution of input PE. This is a typical PE loading steps from host process. In terms of COF loading, the corresponding COF loader does the following steps. It first allocates a memory region for all COF sections and copies these sections to this area. In COF files, section may contain relocation information that specifies how section data should be modified by linker. For example, text section has information specifying what parts of code should be replaced and what should be referenced in memory. For each relocation, the loader looks at its symbol value and determines its type. Based on the type, it applies necessary relocations, like putting address for an internal function or importing an external library. After all relocations are done, the loader gets the go function and starts the execution from there. In addition to COF loading, COBOL-Strike implements a set of functions that can be called from the beacon object files. Therefore, by implementing those internal functions, the COF loader can support both loading too. There are different shellcode implementations for loading PE files and maybe COF files. Normally, one can implement those steps directly writing an assembly code that doesn't have any position dependency, or one can turn any PE file into a shellcode with different tools or techniques like PE to shellcode or donut. Instead of coding these loaders like that, I used a different approach called C to shellcode. Specially crafted C code can be compiled into PE files living fully in its text segment. Therefore, extracting the text segment means obtaining a position-independent code. The conditions for such C files are as follows. There should be no global or static variable in the source code. You should pass all needed global variables as parameters to the functions. All hard-coded strings in the source code should be stack strings, meaning that they are not placed into our data and they are pushed to the stack char by char. And external WinAPI functions are called after resolving them dynamically, which means we need to parse load library and get proc address from loaded memory modules and call these functions for all required external functions with the predefined function signatures. After arranging the source code of both PE and COF loaders by using a compiler, we can obtain such a PE file, whose data only resides in the text section. Garbage code generation and its random insertion is one of the most powerful ways of increasing probability space, and as a result, it is one of the key aspects of polymorphism. Shoggoth supports garbage generation and its insertion into the different places of the encrypted output. Different types of garbage instructions that Shoggoth supports are jumping over random bytes, which you place a jump and random byte chunks, and jump instruction redirects execution flow to the end of this chunk. Generating fake functions with prolog and epilogue, as you can see. Pair instructions for preserving the value, like double NOT, adding and subtracting, or shifting right and shifting left. Jumping over valid instructions. It is similar to random chunks, but this time instructions are valid. Arithmetic operations for a register before restoring the value, like saving its value to the stack, doing random operations, and popping its old value back to the same register. Lastly, safe instructions that change nothing, like NOP instruction, or XORing with 0, or conditional moves to the same register. Combining those types of random stubs or recursively generating them will help to create different byte sequences for each encrypted variant. Of course, to generate these different stubs, Shoggoth uses the Asmjit library. Shoggoth provides two different encryption options, and the first one is the RC4 algorithm. By default, it creates a random encryption key and uses this random key during the algorithm. For decryption of it, Shoggoth uses an RC4 assembly implementation and randomizes the registers that will be used in this decryptor each time. When the decryptor is ready and is generated by the Asmjit, the decryptor is combined with the encrypted payload stub, so that during the runtime, an encrypted payload could be decrypted. Another encryption in Shoggoth is random block cipher. In this encryption, Shoggoth first divides the input into equal parts with the size of 8 bytes. And for each block, it randomly selects an arithmetic operation, an argument with random register. That selected operation is applied for the input block, and reverse of it is generated for the decryptor via the Asmjit library. At the end of this random generation and encryption operations, Shoggoth generates a decryptor stub which includes lots of arithmetic operations with no loop logic. After all these technical details, the generic execution flow for an input file is this. By default, Shoggoth first combines the precompiled loader shellcode according to the chosen mode and the input file. It then adds multiple garbage instructions to this new payload. The stub which contains the loader, garbage instruction, and the payload is encrypted first with RC4 encryption and then with randomly generated block encryption by combining corresponding decryptors. Finally, it adds the garbage instruction to the resulting block. That final block is directly saved to the disk without putting it into a loader or injector executable. Therefore, the output file is the raw shellcode file which contains the encrypted payload, decryptors, and the loader. Now, I want to do a quick demo about its usage and generated outputs of Shoggoth. For the demo of Shoggoth, I want to generate 3 output files for 3 different modes. I will test raw mode with a shellcode that spawns Notepad, PE mode with Mimikatz, and COF mode with ipconfig.bof from the CS Contextual Awareness repository. I have a simple shellcode executor and it will allow us to inspect the assembly instructions of generated outputs. Let's begin. First, I will start a PowerShell in the directory with Mimikatz, a shellcode that spawns Notepad, ipconfig.bof, and the Shoggoth binary I compiled earlier. Before encrypting these 3 files, let's take a look at the parameters and features of Shoggoth with the help flag. By giving the required parameters, you can see Shoggoth's help menu, get more detailed outputs, give the input file, determine the path of the output, give a static seed value, select the mode, give arguments for COF mode, specify the RC4 encryption key, skip the first or second encryption steps, and decide which parts are being encrypted in the second encryption. For any input file, mandatory flags are input, output, and mode. Let's encrypt the shellcode first. I'm selecting the raw mode, and Shoggoth won't end loader for the encrypted shellcode. Then I will encrypt the Mimikatz with the PE mode so that I can run it as a shellcode. In addition to these mandatory flags, I'm selecting the encrypt only decryptor option for the block encryption to decrease the overall size. Lastly, I will encrypt ipconfig.bob file with the conf mode. With that option, I will be able to run this file as a shellcode, just like in Mimikatz. To test the encrypted outputs, I will run a simple shellcode executor from Visual Studio in debug mode. That project will read this file path and execute its content from an executable region. Also, this function pointer will help me to trigger the shellcode. Let's put a breakpoint where the shellcode is started so that I can follow the outputs from the disassembler. Let's start with the encrypted version of the Notepad spawning shellcode. These are the garbage instructions that Shoggoth generated. They will not have any effects on payload or encryption. After the garbage instructions, we will reach the decryptor of the random block cipher. As you can see, the random block cipher consists of arithmetic operations, uses the registers randomly, and performs the decryption operation without using any loops. At the end of the code, there is a redirection that triggers the decryptor of RC4. Let's put a breakpoint and follow this redirection. This new code block is the assembly implementation of RC4 encryption, and that decryptor will decrypt the payload and another garbage stub. So let's continue until the end of the RC4 decryptor. After the end of the decryption process, we again go to another garbage stub. And we get our input shellcode. After this point, we can step out and observe that Notepad is opened. This time, let's do the same steps for the encrypted BOB file. I'm changing the input file path and restoring the shellcode executor project. As you can see, first garbage stub is different than the encrypted Notepad shellcode. You can see the block cipher, it's different too. Let's look at the RC4 decryptor. In this case, it uses different registers for the decryptor. If we continue, we can reach the garbage instructions and the conf loader. After stepping out, ipconfig output can be seen in the debug console. Lastly, let's run the encrypted Mimikatz directly and observe its interactive terminal in the debug console. Run the copy command and exit command to close the terminal. That was the end of the demo. Let me turn back to the presentation slide. Before I finish the presentation, I would like to talk about what I have planned for the next versions of Shoggoth. For now, I didn't put so many garbage instructions to all parts of the output code. Therefore, for the next versions, I'm planning to implement and add different types of garbage instructions and place them to the different parts of the code. Especially for the RC4 encryption, I will try to make it polymorphic. Although currently tool doesn't give so much space for custom stubs, I want to implement an option for custom loader selection and improve the existing loaders. In addition, I want to implement a byte blacklist approach so that selected bytes will not be in the output file. And last but not least, I will welcome every pull request for the improvement of Shoggoth. That was the last part of the presentation. I hope you liked the tool. You can access the source code from the link below. After compiling it with Visual Studio, you can start to use it. Thank you so much for watching.